So if this pops up, this will put a blank, a black bar across. You just come over more by, oops, shifted a little bit, sorry. Just hide floating across. So it's a little worn out. This is forward.
And then back.
And that's back. Okay. So forward back.
If there's a video, do we have to click it?
Yeah. If there's a video, unless you set it up that when you hit forward, it plays it. Usually, you guys have a video?
Yes.
Which slide? Which slide is your video? Right there?
Yeah, that's
So, what you're looking for, of course, is this one. The video start right here.
yeah.
Unless you got it set up so when you hit next, and it goes to the next slide, thing to keep in mind is sometimes hitting next restarts the video, in which case what you got to do is come down to the control down here, which is the PowerPoint control for the next slide. But that's only if you hit that and suddenly it starts repeating, then you have to stop it. Just come down here.
It's the audio.
It should be. I mean, if the audio is up, it should be. So that's what I want to do. Just stop there, we're going to get you to start. Make sure you got sound down there. Sound down there.
Together, so have the mic.
You guys are good. I'll give you everything.
Thank you.
I'm going to start. All right, everyone, please take your seats. We're going to start with the next presentation. All right, is everybody ready? All right, go ahead, team.
Good afternoon, everyone, and thank you for joining us. We are Team Rooftop Candidates, and today we'd like to present our project, Determining Ideal Rooftop Candidates to Host GPS Error Correction Devices. So this is our team. I'm Kirabel Tadessa. I am a developer for this project. And these are our partners. We have Dr. Lance Sherry, as well as Dr. Rudy Sultana, and our instructor, Dr. Amartya Bhattacharya. So GPS, or Global Positioning System, is a type of satellite-based navigation system that we use and rely on a daily basis. GPS works where there's satellites up in the Earth's orbit that emit a radio signal that our phones or our other receivers receive, and then there's a calculation that's done and processed, and that different signals from different kind of satellites triangulates our location with a calculation. Once this is done, there's a lot of error that's introduced because as the signal is coming through, there's the ionosphere, there's different distances that it's traveling, so there's many variables introduced. So there's about a 33-foot radius of error with that signal. What that means is if you're standing in one place, your phone could say you are anywhere within 33 feet away at times. And this can be worse if you are covered or if there's any more interferences with the signal. So why is this significant? So when we're just looking at our phones, when we're walking, we might have noticed, hey, it's saying I'm across the street, or it's saying, somewhere I'm not supposed to be. Well, that can be a minor issue, but imagine, you're a pilot flying a plane and in very bad conditions. It's super cloudy, a lot of wintry mix, and then your GPS on the navigation, that's the only thing you're relying on, but it says you're 33 feet away from where you're supposed to land, that can cause catastrophic problems. And we also hear in the news every day that, there was a person who followed their GPS and they, drove off a bridge, or, any kind of errors that come with GPS we hear can be catastrophic. And there's also so many technologies like, drones that we use on a daily basis as well nowadays that really requires higher levels of GPS accuracy. And that's where GPS error correction systems come in. And so imagine from that 33-foot distance, we're able to bring it down to about 3 inches of GPS error using these different error correction methods. And there's several different error correction methods, including post-processing of the signal and others. But really, we wanted to focus on real-time kinematics, or RTK solutions for our discussion today. So RTK is basically where you have a single device that you put at a specific location, and that it's basically like a fixed point, a grounding point for the signal. It receives the GPS signal, and it emits the corrected signal to our phones. There are several different limitations with RTK that we'll cover, but for now, our problem is to identify the best possible rooftops to host an RTK base station within a given market or area. Now, these several considerations that we have to make is that an RTK base first really has only about 6 to 18 miles of radius. So if you put an RTK base at a certain location, then you need to have, you need to be within that range to receive that error correction. So you're going to need multiple if you're looking at a wider range of area. The other thing is that our RTK, it requires visibility to a minimum of at least 5 satellites at a time. So the best place to put these is on rooftops where there's a clear view of the sky, where you can get access to at least 5 satellites that are giving their signal to be corrected. And there's other considerations, including location, so as the rooftops that we mentioned, but also are we even able to place these devices on these buildings? So is it a government building that's just not going to allow us to add an RTK device? Is there proximities to, so are we having multiple RTK devices close to each other? So one thing is, if you have multiple devices close to each other, you're not going to get even better than 3-inch correction. It's just a waste of money and resources at that time. So we really have to factor that in. If there's already a device there, we don't want to keep adding more devices there. And the other thing is the cost. So going along with the last point, like we want to minimize the cost, but increase the error correction as much as possible. And so to cover some of the details, we'll go into the project objectives with Pranav.
Hello everyone, this is Pranav. I am working as product owner for this team. The main objective of this project is to identify the best rooftop candidates to host an RTK base station by analyzing the dataset and using tools like PGAdmin and QGIS. And the second objective is to visualize the things like precision, and we are using some technical terms that will be explained by my friend Sabri.
Hello all, this is Sabri Mukunjaram. So I worked as a developer for this project. So there are like some key terms like which I wanted to talk about before entering to our actual project. So these are the 3 technical terms which we will be using frequently in our slides. So first one is the horizontal profile. So the horizontal profile is nothing like we'll be taking our rooftop and we'll draw a 360 lines, and each line represents 1 degree. So this allows us to this analyzes whether the source building is getting interfered with another building or not, and this will be a crucial thing to host an RTK base on the particular rooftop. So the second one will be the angle of elevation. So to explain it in a more simple way, let's imagine like a person is looking to a top of looking on a top of a building. So the angle between the ground and the line of his height is the angle of elevation, and this plays an important role. This will be playing an important role in our project as well. So the third one will be the sky visibility. So as Kirban mentioned about the RTK base to be having a much more clearer sky visibility, the more sky visibility will be a good one. So it's like we assume a dome-like structure on the rooftop, so which allows us to see whether whether it covers most of the sky area and it does not interfere with any other aerial or like any other building nearby it. So these are the technical terms which we will be using. Next, Aaron.
For our project, we are having two data sets, that is buildings data and terrain data. Coming to buildings data, the building data contains of height footprints for 2,834 buildings in the GMU campus area. And coming to terrain data, the data is shown up in the shape of the land like hills or slopes. And the combination of data sets we can find the elevation height. And after the simulation of both the data sets, we can find the precision. And both the data sets combining, we gonna get the 360-degree horizon profile for each rooftop. And there will be a short demo.
Hi everyone. In this quick video, we'll see why absolute height matters even more than just a building's height off the ground. First, building height measures the distance from the ground up, great for architects and elevator shafts. But imagine you're launching a drone, tracking satellites, or worrying about flood levels. That's where absolute height comes in. It's the altitude above sea level. Imagine a couple of 50-meter towers can sit on hills of different elevations. One might actually be 200 meters above sea level, the other only 20 meters. For things like GPS accuracy, radio coverage, and flood safety, it's that sea level number that really counts. As demonstrated in the 3D visualization, comparing models built on ground level height versus true elevation above sea level reveals significant differences in horizon clearance and coverage. By incorporating verified absolute heights, we can proceed with full confidence that our calculations accurately reflect real-world conditions.
Hey everyone. Now I'll explain about the steps involved in our analysis. In the first step of our analysis, we found the centers of each building. And for the buildings which have irregular shape, we choose a point which is closer to being the center for that building. Next, we found the horizon profile for the buildings. So imagine this: if you're standing on a building and you're turning in a full circle, and you're drawing a straight line in the each direction you face for each degree, then you will have 360 lines for this full circle. So these lines are called horizon lines. And for the GMU campus, we found the horizon lines, and we did it for the 30-kilometer radius. So like this is one of the building in GMU campus, and we projected the horizon lines and for 30 kilometers. Next, we identified like where these horizon lines are getting obstructed. Like if there are any taller structure, these lines will get obstructed, and if like there are any smaller structures, these lines will not get obstructed. Knowing these points will let us know where the building, where the line of sight is getting blocked. Next, we calculated the distance between the main building and the obstructing building, and then we found the angle of elevation. Then we added all these angle of elevations to get the blocking angle. If the blocking angle is lesser than 10 degrees, then we can say that the rooftop has good sky visibility, and if the angle is greater than 10 degrees, then we can say that the rooftop doesn't have good sky visibility. Now, Sabri will continue.
Thank you, Arun. So I'd like to say a brief explanation about the visibility score. So that so before talking about the visibility scores, look, so we had a conclusion that before considering this factor, so we were like finalizing our rooftop candidates and all. But we wished, like when I was like personally looking through the QGIS, and we were able to see like multiple potential buildings were like not listed in the potential candidate. So we needed another one factor which will finalize, or like which will make us to make sure that every single potential building is being enlisted in the potential rooftop candidate list. So for that, we used a term called sky visibility score. So before talking about the sky visibility score, I'll be saying like what is the sky visibility. As I said earlier, like the more open sky is the sky visibility, and to know like to consider this, we are using this dome-like structure on every building's rooftop. So when this dome is getting interfered with any other buildings or like any other aerial objects, then it is considered as interference, and those interference are recorded. So the scores of the sky visibility score falls under 0 and 1. The 1 is the perfect score, which is the which has the which says like the rooftop has the much more clear sky, and the lesser then it might be a potential candidate, but we are just omitting for now because for this time constraint we have to also include multiple other things also. So next, so in order to put all the things like into a simple words, let's consider that we are installing a router inside in a home, and we are sitting inside a room and we start working. So we can like sometimes we will be noticing that the Wi-Fi signal drops or the Wi-Fi will be weakening because of the because we will be working inside the room and the wall is an interference. So here the Wi-Fi router is the building rooftop and the spherical dome which I was like talking about, and the signal is the RTK signal which is coming from the satellite. The GPS signal from the satellite, and the wall is the interference, which is like the other buildings or like any other abstraction which I was like talking about. So I would like to hand over the session to Vyoma to discuss about the results.
Hello everyone, I'm Vyoma Harshita Padapati and I'm a developer for the project. Now that we have calculated the blocking angle and the sky visibility, we move on to narrowing down our whole data set to find the most eligible rooftop to place these RTK base stations. Our approach has been quite selective, where we have assessed all the buildings in the GMU, in and around the GMU campus for 360 degrees and made sure the each building's height is greater than 150 meters and the blocking angle does not exceed 10 degrees. Also making sure that the sky visibility score for each particular building is 1. As you can see, these green buildings, those are our potential candidates. So once we have filtered out using the above metrics, we came up with 49 buildings in the GMU campus, and these green buildings that you can see right here are the high potential candidates in and around the GMU campus. Once we had our potential buildings, we move on to our next objective, where we have created 3D polar plots representing each of the high potential candidates buildings sky visibility. Let's consider this. Let's consider this as the roof, potential building, and this circle represents the 360 degrees. For this particular building, you can see that we have obstruction only in one direction. So except in that one direction, the building has clear visibility in every direction around. In the next result, you can see that we have multiple obstructions in all different directions. The obstruction could be just 0 degrees or 1 degree or 5 degrees, as you can see. So these are the buildings with multiple obstructions all around in all directions. This is the tallest building in and around the GMU campus, and since it's the tallest building, it has no obstruction and it is the most suitable to place the RTK base station. And this is the water tank in our campus. Let's now quickly look at our demo.
Hello all. Today, we'll walk you through two main objectives: how we approached the problem and how we selected the best terrain data onto a map. To do this, we used a mapping tool called QGIS. This is the QGIS interface. In the lower left, you can see the layers. Here, we've added both the buildings and the terrain data. However, we couldn't easily tell where everything was on the map. To fix this, we used a plugin called OSM Standard, which stands for OpenStreetMap Standard. As you can see, it covers the Fairfax, Baltimore, and Washington areas. We decided to focus on the GMU campus, since we were familiar with its buildings and it made team communication easier. We trimmed our map to a small rectangular area around the campus. Here, you can see the GMU campus. Next, we needed to select only the buildings inside this campus area. For that, we used a database tool called PostgreSQL with a management console called pgadmin. Using this, we filtered out just the GMU campus buildings. Then, we needed to find the center of each rooftop. Using pgadmin, we generated several layers, including the rooftop centers. Checking the right layer lets us see the rooftop centers clearly. The next step was to draw 360 lines from each roof center. One line for every degree in a circle. It is to check if nearby buildings might block the rooftop's view of the sky. These lines are called horizon lines, each representing 1 degree. Along with this, we also compared the heights of nearby buildings and recorded everything in a database table. To show you how it works, we used Merton Hall as an example. Here is the horizon profile for Merton Hall. Its absolute height is 152.2 meters. Next, we looked at which buildings these lines hit. When we added the layers showing intersection points, we found that only a few buildings were tall enough to interfere. Most were too short to matter, making Merton Hall a strong candidate. After that, we needed to measure how much each interfering building blocks the rooftop's view. We used simple geometry, applying the Pythagorean theorem and a formula based on tan inverse, to calculate the blocking angle. We also recorded the distance from the roof center to each blocking building. Each individual blocking angle was saved in a database table like this one. Finally, to choose the best rooftop candidates, we considered 3 key factors. 1. The rooftop's height, it must be greater than 150 meters. 2. The blocking angles, each must be 10 degrees or less. 3. The sky visibility score, it must be perfect, a score of 1. Based on these criteria, we found that out of 2,834 buildings on the GMU campus, only 49 rooftops are eligible for hosting an RTK base.
Good afternoon, everyone. This is Varshita Lingamneni. I'm a developer of this project. So let's just wrap things up very quickly. So first of all, our project is all about solving a pretty common problem that most of us really don't even realize, that GPS isn't accurate in many times. So this is actually a problem when we use self-driving cars or like surveying anything, or when we are using a drones. So to do this, to correct the GPS, we are using an RTK stations. These are the small base stations which are placed on the rooftops so that the GPS will be corrected precisely from the feet to the inches. So to do this, we have used 2 data sets, building data and the terrain data. With this, we have come up with the potential buildings by using the sky visibility, absolute height, and also the blocking angle. So apart from this, we also did the 3D polar plots of the potential buildings, which are 49 buildings and 2,834 buildings, which we have around this. So for all those 49 buildings, we have visualized the 3D polar graphs, which is used for the sky visibility on top of every building. So in this way, we have not just developed the GPS correction rooftops, but also we have given a smarter way for it. So coming to this, in the future steps, we can actually scale this project, not just by relying on the rooftops. We can just even use the real-time satellite data. As of now, we just used only the static data. It means that if you're selecting a rooftop, then we have taken the data on the static satellite. As we all know, the satellites move around. So to be it more precise, like wherever or at what time you're going to use this, it's going to be more precise instead of just taking a base as a rooftop. So, and then we also want to automate this workflow, because if if you want to do this for overall USA, it's going to be huge. It's in that case we call it as a big data or something. So to automate that, we have to create a pipeline in the future so that it will be helpful for a lot of industries as well. So, and the last one is, if suppose our client, Mr. Rudy, he wants to use this rooftops, not just for USA, maybe for other country in the future, we just will be creating a website. So in that website, whatever the data which has been automated in our future step will be taken into that website. And if he wants to go and select a building from there, it just pops up and shows that is it a potential building to place the rooftop or to place the RTK or not. So that's all regarding a project. Thank you everyone for listening, and we are open for questions, what you have. Thank you.
All right, we have a question online from June Huck. June Huck says, maybe I missed it, but I feel like what RTKs are was not properly explained what they are, or at least wasn't explained until after they were mentioned on the problem statement slide. Can someone on the team please just clear up what they are and if this is the primary only way to get consistent GPS data?
Yeah, so RTK is basically a device that you put on top of somewhere where you can have good sky visibility, or basically on rooftops if you're in kind of an urban area. And it is used for GPS error correction, but it's not the only method of GPS error correction. You can do something called post-processing, where the signal is processed post, while RTK is doing it in real time, which real-time kinematics is what RTK is. And basically how the device works is you have that one device, it's in a fixed location, a known location, a known rooftop, and it gets the satellite signals, and that RTK device is able to send the corrected signal towards our phones or any other receivers within its range. So it has that 6 to 18 mile radius, and that is how the RTK device itself works. But it's one of many GPS error correction methods.
All right, another online from Pravan. How does RTK performance vary with partial sky visibility in specific azimuth sectors?
So the sky visibility matters, like, because the more sky visibility is, the better the output would be. Like, let's say like a rooftop is like 0.9, it scores like 0.95 of the sky visibility. It might be a potential candidate if it is having if it has the height of like 150 meters or like above that. Then the RTK might give us potential output like which we are expecting. But let's say the height and other factors which is depending for selecting a rooftop candidate is less than or like it is not matching the criteria, then the RTK might be underperforming, and that might be an issue again.
All right, this is from an anonymous attendee. Directed towards Pranav. Can you explain the primary objective of your project, emphasizing specifically how it resolves the fundamental limitation in existing GPS accuracy methods within dense urban settings?
The primary objective is to identify the best rooftop places to host an RTK base station, and then we want to analyze the data set, and then after using tools like QGIS and PGAdmin, we are helping in the terrain and another data.
Another anonymous question. Based on your analysis, why was Merton Hall identified as the optimal rooftop at GMU Fairfax campus?
Merton Hall is one of the optimal rooftops, but we also have other buildings. Like I mentioned before in the results, the tallest building on campus and in and around the GMU is the water tank. And then we have Merton Hall, and then we have Horizon Hall. So these are some of the potential buildings for in and around the GMU campus.
To add on the one more point, so we were like familiar with the Rafanog and the Rafanog and Merton Hall, JC and all. So we just kept our analysis on every buildings which we know, and we just started looking around for the potential buildings based on these criteria. And Merton Hall was like the one building which we usually see when we enter the campus. So we just took as Merton Hall as an example so that everyone will know about which building we are talking about. So, yeah.
Okay. Mahendra asks, how could your methodology be scaled to analyze larger urban areas like Washington, D.C.?
Yeah. So what we can do is for larger area, we can create a grid. For example, we have a DC area, and we can create 9 grids. And for the each grid, we can apply what we applied for the GMU campus. So for each grid, you'll find a potential building. For instance, if this is the DC area, we'll make 9 grids, and for the each grid, we'll find the best rooftop candidates, and that way we can scale up our approach to DC area.
Just to add to what my friend said, if we have the potential, if we have the computational power to run large data sets, we could just do it without dividing it into grids. But if we don't, if we're just doing with our PCs, then we can scale up by dividing the whole data set into grids and try and customize each grid, try and analyze each grid and combine the whole data set at the end.
To concise it all, so we have the base code for the GMU campus which we approached. So it's like we just need to improvise based on the polygons. Like for this polygon does only have the GMU campus what is that, the coordinates. So let's say if we scale it up for DC area or like some other data set, and we see if we give the coordinates for it and change the variable names for that. And we have the base code, and we can just automate it based on that. Yeah.
Are there any questions in the audience?
Yep, there's one over here. Long time coming. Oh, yeah, this. Go ahead.
So overall, the presentation was good. So did you guys think about if there is a change in the atmosphere, Earth's atmosphere, will it affect the placing strategy for the RTK?
No, it wouldn't. So when we're getting signals from the satellite, in the atmospheric dome itself, they bounce and bounce back into the Earth's atmosphere. So that is why we are doing the dome calculations to dwell deep into that. So once we have the score, then it wouldn't matter if there is any obstruction or if it's raining or if there is a problem in the atmosphere.
To add one more point for that, so it's like the dome sky visibility dome calculation thing has like much more intense in that. So we don't have because of the time constraint, we just stopped up to the part where we get the sky visibility score. But there are like some certain criteria which we need to be considered if we are scaling up and all. So that will effectively reduce the what is that? Effectively reduce the number of potential candidates, or it will give us the it will narrow the path of search for getting a better rooftop candidates. So on your question, that factors also will consider the atmospheric pressures and all.
All right, that's all the time we have for questions for this team. Thank you, team.
Thank you all.
All right, Team Recidivism 10, please meet me at the stage. Remember to, for the folks online, you have to speak right up against the mic, right? You can split it up.
It's gonna work if it's like anything else. But this shows up, right, recording controls, nothing like it. Fast enough. Right, so, forward. Video, this is set up to create video in advance. So we have a video control. If we try to advance it, it plays the video, and you have to come down here.
All right, folks, settle down. All right, go ahead and get started, please.
Yeah. Good evening, one and all. This is Team Recidivism Problem Ingestion and Evaluation. Currently, we'll be showcasing our final presentation of our project. Coming to the next slide. This is our team. Myself, I am Jagdish. I worked as a Scrum Master for this project.
I'm Vinay. I'm the product owner for my team.
I'm Srija Anasuri and I'm developer of this team.
I'm Sahit Reddy Suram. I'm developer of this team.
I'm Raghu Manjunatha. I'm a developer in the team.
I'm Gnaneshwar Devanmali. I'm developer of this team.
Yeah, coming to partners and collaborators, federators, professional writing, communication and research organization. They are our clients. And coming to collaborators, we worked this project with George Mason University, College of Engineering and Computing, with the Department of Data Analytics and Engineering under the guidance of Dr. Professor Isaac Gung. Coming to the next slide. Before saying the problem statement, I just want to clear what exactly the term recidivism means. Recidivism refers to the tendency of previously imprisoned individuals to reoffend and return to the prison. High recidivism rates leads to prison overcrowding, social instability, increasing the public cost, and finally, failed rehabilitation efforts that are made by Bureau of Prisons. Coming to the next slide, the main problem statement is like Federal Bureau of Prisons are struggling to evaluate the better effective programs due to staff shortages, technical limitations, and budget constraints. The solution approach to our project is like we have to build a data-driven evaluation system that has to classify ineffective ones and effective ones, and ensure evidence-based policy decisions. And my friend Sija will be continuing.
Thank you, Jagdish, for clearly explaining the problem statement. Now let's look at our 4 key uses of our evaluation platform. First, we have criminal justice industry member. So what this person does is reads the program data and tries to understand its impact. Next, we have the program submitter who uploads the documentation related to the recidivism reduction program for evaluation. Next, we have the BOP reviewer who reviews the submissions and then either accepts or rejects the program based on the assessment. Next, finally, we have the system administrator who makes sure the infrastructure is running smoothly. Coming to the next slide, so let's dive into the data sources. So during our initial exploration, we looked into data sets like NIJ recidivism challenge data set and the Iowa data set. Then we also consulted the GMU Department of Criminology for academic guidance. But then later we had to transition into NLP-driven evaluation pipeline. So we had to shift our focus accordingly. So here comes our core focus data set. So we were provided over 50 plus meta-analysis papers by our clients, which is Fred writers. So these papers are drawn from peer-reviewed journals, government publications, and policy reports. And these research papers cover various recidivism reduction programs like cognitive behavioral therapy, drug treatment, and more. Coming to the next slide. So this is our end-to-end pipeline, which we used for our project. So I'll just give an overview of what we did. So our pipeline begins by mounting the research papers that we were given, and we extract the raw text from these papers, and then we clean the text, and then we chunk that text. Then later we generate embeddings of these chunks, and then we store them in the ChromaDB. And then we have used HNSW graphs and cosine similarity for similarity search. Then coming to our modeling, we have used BERT model, and then we have used the T5 model for generating concise summaries when a user sends a query to our chatbot. Then we have used Streamlit for our front end, where the user can upload a PDF or query the chatbot or can manage the files. Next will be continued by Raghu.
Thank you, Srija. So the whole system architecture might look overwhelming to understand all at once, so we'll break down into simple sections. The very first section that we're going to dive in, the foundation for our whole project, starts from data extraction and pre-processing. The first step, when we got the PDFs from the client, the thing that we observed were few PDFs were digitally typed and few PDFs were digitally scanned. So we wanted to build a universal pipeline which can extract text regardless of the origin point of these PDFs. So this pipeline inspects initially using PDF Plumber and extract text if the PDF is digitally typed. If in case it fails, it falls back onto the OCR. We gave Tesseract and PDF to images, which converts those PDF pages into images and extract text from those images. So once this is done, then we went for text cleaning. For text cleaning, we use regex, regular expression. So regular expression initially removes all the headers, emails, URLs, white spaces in the text. And then we went for text chunking. Text chunking worked for us because future will be using embeddings and LLMs. They have a window of being text should not exceed more than 500 tokens for them to work well. So we chunked it from 300 to 500 tokens per row. Then after chunking, we went on structuring it. We structured in a uniform metadata format of having the file name, chunk ID, and chunk text. Going to the next slide. Once we extracted all the text, now we wanted to convert all those text into numbers or vectors. This process called embedding. So for this, we used a sentence transformer module called as all-mini LM L12. It converts text into numbers in 384 dimensions. So it is very accurate for the LLM to grab one which requires when it is when a user asks a query. And also it preserves the context of the text instead of going for an exact conversions. So once the conversion is done, then we wanted to save it in a vector database so that we don't need to rerun all the embeddings every time. So we stored it in ChromaDB. It's a lightweight, open source, and also have a better semantic similarity search features. So once we stored everything, we co-located all our embeddings right next to our metadata uniformity. So coming to the next slide, you can see the screenshots of both extracted and embedded files. They have the same uniformal metadata where file name, chunk ID, chunk text, and embeddings come right next to it. So this helps us when LLM comes up with a query and it finds an exact chunk, we can easily trace back the originality or the source of the whole file. And coming to the next slide. So once we're done with the embedding and storing it, we wanted to add some features for it to make the search more precise, accurate, and fast. The first thing that we added two features. One is HSNW. Second one is cosine similarity. So HSNW means hierarchical navigable small world. It's an algorithm that works inside ChromaDB where it finds the exact contextual text chunk more fastly, and also it does nearest neighbor search, so it grabs chunks both behind and forward of it. So once it finds the contextual chunk, then we added cosine similarity for it. So cosine similarity measures the vectors based on the angles between them. So it catches on to the exact contextual chunk so that it answers the LLM query more accurately. This lays the foundation for our whole LLM formation. So moving on to the LLM, Gnaneshwar will take your role.
Thank you, Raghu. So coming to the LLM, as Raghu said before, after checking our text, now it's time to classify them. So for that, we are using the BERT classifier. The reason to use BERT classifier is it is very good at content and semantics. So these two are very important when you guys process the research text. So Bird takes these text chunks as an input and provide uh, predicted labels as output, and these predicted labels are saved in a pickle file, so that they can be used for further search and filtering. Coming to next slide, or after retrieving the relevant data, we use T5 for summarization. Unlike Bird, which is a classifier, we use T5 because it is optimized for text-to-text generation. So it is good to summarize the chunks. So when we get top k chunks from our model, we give them to T5 so that it summarizes and give a human readable content. And coming to the next slide, to bring everything together, we created a front end by using Streamlit. So it contains three tabs: chatbot, PDF uploader, and manage files, and also the front end is connected live to our embedded models and ChromaDB and T5 for the live interactions. So we also use Google Drive for our storage, so that during the collapsation, the data cannot be lost. And my friend Syed will continue from now.
Thank you, Gyaneshwar. Now we will dive into our working demo. Play.
Well, coming to the working demo, when a user want to interact with the Perseverism dashboard, chatbot, or he can use the above link to access the chatbot. If after access the link, he can see the UI of this type, where he can see the current documents, which is of 8,668 documents. And below that, you can see the three tabs. One is chatbot, PDF uploader, and manage files. We will go each tab in depth. In chatbot tab, we can see the two drop down. One is file, and other is top k documents. And in the input section, we can ask any questions like the impact of college education in prison. Then we can, if we hit submit button, it will run the code in the backend. As you can see from the top, it's running. It will take time, but eventually it will get the results. As you can see the output now, here the output is coming from the three documents, as we selected the top three documents here. So that we are seeing the three bar plots here, which first bar telling us about which file it's coming and what is the similarity score. As you can see, the first result is coming from a correlational educational residuum towards tool for education, and second is coming from the same file as well with a similarity score of 79%, and third one is also coming from the same file. As we selected the all files here, it will get the result from the all files. If you want to, if we increase the documents per 4, top, it's running, and yep, now you can see the results is coming from the 4 documents. The first 3 are same as the previous one, what we have seen, coming from the same file. The fourth result is coming from the education meta-analysis with a 78% similarity score. But you can see, we can also get the information from the single file selection. As you can see, the correlation educational residuum file. We can select the ping file here and ask the same question, and hit the submit button. Then we will get the output. It will take some time, but yep, you can see the output of which is coming from the 4 documents of same file. as you can see the output, if we see the response, college coming from the three documents, college education during incarceration has a greater impact on recidivism, a review on the research on correlation education and the impact on the recidivism, and the pioneering. We will get, and if we go to the four documents, the college education during incarceration has a greater impact on recidivism, a review on the research on correlation education and the impact on the recidivism is needed. A cost analysis suggests correlation education can be cost effective. As you can see, as the documents increases, the result is more accurate, and you can see the file coming from the one file, results coming from the one file. And if a user want to upload a new file, you can do it by simply selecting, going to upload option tab and select. I'm currently selecting the one file, Vira one file, and hit pen. You will see the two messages like file uploaded successfully and one more extracted Vira one file into this this file. So if we want to see the change in the current database, you can rerun the file or simply remove this file. Now we can see the file current database as 8,708 documents. And if we want to ask any questions from this file, you can come back to chatbot and select that file and ask the question like, does program reduce recidivism, and hit submit button. Then if you can see the output on the question and answer history. So the next question will be the question 4. Yep. Will take some time. Yep. You can see the output. Like every dollar invested in the prison based on recidivism and educational meta-analysis, more than $4 in the important employment savings recidivism. People who participated in the college and prison programs were at least 66% of offender rehabilitation. Basically, it's saying the program are not effective. As you can see, the documents are 4 coming from the same file. We are getting the more accurate results. If a user want to select delete certain files, you can go to the manage files tab and can select 1 or 2 files. How many you want to delete? I want to delete 1 file. Now you can see that for message saying that we found 40 documents matching the selecting file. Then hit if we hit the select delete select documents, we can see the 40 documents as deleted. In order to reflect that in the current database, you can simply rerun or remove this file. You can see that we have come back to the same document we have previously. Then if we want to test whether whether our UI is suitable for negative documents not related to recidivism, we can ask what is photosynthesis like questions, and we can check whether we are getting the output or not. You can see that the message coming down that the answer cannot be determined from the available files based on the current database. The same thing will be stored in the history. Yep. After doing the entire analysis, we can hit the done asking questions, and we can exit the system. Yep. Thank you.
Yep. And now that we have seen the working demo, now we will understand how the end-to-end system works.
Hello.
Yeah, end-to-end system works. In this this slide shows the visual representation of our chatbot. When the user gives an output input to our chatbot or any question to a chatbot, it goes through the text embeddings where it converts the text into a numerical form and vectors. To do this process, we use BERT model where it is used for calculating the understanding the semantic meaning of that input. Then the meaning when it understands the meaning, it goes into the semantic search where it understands it calculates and see whether what documents are matching to our question. To do more efficient way, we use an HNSW question similarity. These are the technique used that do faster vector search and improve the neighbor search, and based on that, it will take the top k similar values, top k similar documents based on how much we select, 1 or 2 or 5. Then based on that data, it goes into the T5 summarization, where it summarizes the entire text and the entire documents what we have, what we got. Then it goes then it will display our in a proper response, in a user can see the proper response and visualization of analytical answers like that. Coming to the next slide. In this slide, we'll see the how PDF uploader works. When the user gives a new file to the system, it goes through the universal pipeline where it searches based on the document, what type of document either it goes through PDF Plumber or OCR or the other PDF. Then after extracting the raw text, we need to clean that and remove the unwanted information. Then it go to regex and goes through do chunking of our entire documents. So as the entire document is too large, so we are doing chunking. Each chunk has nearly 500 rows with the unique ID of chunk ID. Then it will generate a 384 dimension vector in our database. It then stores into our ChromaDB, where we can see in our that reflect in our database. The next slide will be explained by my.
Thank you, Sai. That's a great explanation. Now I'll be talking on schematic flow on how to manage files. So when a user uploads a PDF research paper, the system starts to process it. It breaks it down into chunks and then stores it into the ChromaDB. So if a user wants to delete a file, a particular file in the future, so the system starts to find the chunks, the matching chunks, and then removes that from the ChromaDB. So ChromaDB. So just before deleting, it confirms with the user and then clears it up from the ChromaDB. So the main purpose of this is it keeps the system clean and neat, and it is also easy to use. Coming to the quick summary. So we have built an end-to-end system that can read the PDF research paper, that can understand the contents in it by using the AI models, and then respond back to us in a smart way. So so that to make this work, we used T5 for summarization and BERT as a classifier, and ChromaDB for storing, and Streamlit as our front end to upload and uploader. So coming to the future work, so there are few improvements that can be done in the near future. The first one is a secure reviewer portal login based interface for the reviewers to interact with the chatbot to upload and rate the PDF research papers. And the second one is a scoring ranking system that can be improvised, that can be improved. And also the third one is the security. This is the most important part, the security. So if this platform if this platform is deployed in the real world, then security is the most important part, because security is the most important part, and it can access. That's it. There are any questions? Do it.
I have 3 questions online from Keith Malley. Does the architecture prevent re-ingestion of PDFs that are already in the corpora?
Yeah. So as of now, it does not allow the same PDF to re-upload. It can detect the name of it, but if in case you change the name, it can't detect. So it's something we can add in the future work. So not to allow duplications.
All right, next question from Kristen Connolly, excuse me. Is there a reason you chose to use a gradient on the graphs produced by the chatbot as opposed to making the bars right size to their height?
Basically, those are for the comparison between the two or more. I mean, those are the comparison among the programs to evaluate. It is all about the comparison between the studies of the recidivism reduction programs.
Okay, third question from June Huck. Does the chatbot/summarization models have any methods to try to mitigate influence of biased sources, whether that source is in the corpus or given to the chatbot?
So since the whole chatbot is a secure portal for restricted access in the Bureau of Prison, so it's not going to be live for public. So it's something a person with most encrypted security or responsibility can access. So it as of now that's the whole agenda of it. Yeah.
Are there any questions in the audience?
Yeah, basic question regarding the LLM model which you have taken. I think you guys used BERT, right? Is there any specific reason for it to be taken, and did you try to evaluate with any kind of other models, let's say Llama or any other model? Is there any specific case, because LLM responses are different depending upon the parameters it has? So, any insight on that?
Before confirming the BERT, we used Zobata and different kind of LLM. So while testing them to when we are training them, the the training laws and all those factors were not good enough for us. So when we checked with BERT, we got a decent results. So that's why we went with BERT.
Yeah, I mean, the question was there any like comparison, like LLM response with the other one, so that you choose this over them? Do you have any? Or if it's not, it's okay. Okay.
No, we don't have.
That's fun. And second thing is, where is it all deployed? All the infrastructure architectures.
It is on Streamlit.
Streamlit.
Yeah.
Okay. Are you guys thinking about keeping it in the cloud or something like that? Regarding the, I don't know who's the client exactly is, but regarding the client.
Yeah. I mean, at this point, that is kind of secured one. We just have to deploy it and give that to the client. It
Yeah.
is not open source at this point.
Okay.
Yeah.
And Streamlit is based on your computer, I mean, based on the LAN, or is it internet?
We can use it on cloud as well.
Yeah.
On cloud as well.
Yeah.
Okay, fine. Yeah, fine. Thank you.
Any other question in the hall? Yes. Professor.
More than a question, a comment. I do commend you for the topic, and I have seen other problems. As a matter of fact, some of my teams have used exactly the technical solution that you use, BERT as the classifier and T1 and T5 as the optimized text-to-text solution. So congratulations on that. Very well done. Thanks.
Yeah. Thank you, Professor.
All right, that's the last comment and question. Thank you, team.
Thank you.
Okay, recidivism 11, please meet me on the stage.
Just make sure that if that comes up, hide code meeting controls. Guys, where's my clicker? Who's got my clicker? Come on, guys. I know the team just had it.
Recidivism 10, get the clicker as soon as you can. We need to move on.
Forward. Back. To play a video. Play a video, you'll probably have to, use the mouse to start it. And, if you go this and go to the next slide, and it plays the video again, just go to that button and start it. When you're speaking, for the folks online, make sure it's right up close, right?
And this is for the next.
For the folks online, make sure you speak like right back. Right. Give me a second. All right, go ahead and get started, please.
Good afternoon, everyone. Thank you for being here. We are Team Recidivism 11 and we are excited to show you our project Recidivism Program Ingestion and Evaluation. This project was developed under the guidance of Professor Dr. Isaac Gong here at George Mason University. Our project particularly focuses on evaluating different rehabilitation programs related to recidivism, which actually means the cycle of people returning to the prison after their release by committing another crime. Over the next few slides, we will walk you through the actual problem statement, our proposed AI-driven solution using retrieval augmented generation chatbot, which enhances the decision-making process and also the compliance in a variety of program assessments. Moving on to the next slide, this is our core team of 6.
Hello, I'm Akhil. I'm the Scrum Master for the team.
Hi, I'm Soumya. I'm the product owner.
I'm Sudeep Viradi. I'm a developer.
Hi, I'm Pranavi. I'm the developer too.
I'm Monish. I'm a developer as well.
And I am Vaishnavi, also a developer for the project.
We had the opportunity to work with FedWriters, a company that helps federal agencies through writing, communication, and technology. They help teams by creating technical reports, training materials, policy documents, and much more. They were with us from the very beginning, helping us understand the First Step Act, refine our scope, and stay focused on solving real-world problems. Their feedback helped us think deeper about how recidivism works and how we can use technology in a meaningful way.
Okay, now we're coming to the term recidivism. So, what is recidivism? Basically, it refers to the tendency of a criminal to be to reoffend and then placed back into prison bars. So, recidivism is a very important key metric because of it, we can assess the effectiveness of correctional programs and rehabilitation efforts. So in a state, if there's a high recidivism rate, this is because of the current interventions, or you can say resources, are insufficient. So if there's a high recidivism rate, there's a high crime rate. So this can be a problem to reintegrate individuals into the society. Now, the aim is to reduce recidivism, so such that it can help for public safety, lower costs, and can support successful reintegration of individuals into society. Coming to the problem statement, the Bureau of Prisons, or you can call it the BOP, in the past has used manual validations of reducing recidivism programs. But because of this, there was like delays, high costs, and most importantly, compliance issues. So based on our client requirements, we proposed an AI retrieval augmented generation, or you can call it a RAG system. So a RAG system, with the RAG system, we integrated MongoDB for structured storage and the FICE for efficient document retrieval. So now we have around 50 research papers. And we use NLP techniques to extract key insights for program evaluation. So each paper has different methodologies, such as the ACT, the CBT, and the FSS officer training. So this solution will automate assessment, improve decision-making, and it leads to effective recidivation program evaluation. Design and impact. So our mission is to design an AI-powered system that improves correctional programs by automating document analysis and supporting compliance with the FSA. So coming to the vision, we envision a future where smart technology can at least tune to empower the justice system such that it can reduce recidivism, promote rehabilitation, and successful reintegration of individuals into the society.
So coming into the system architecture, so currently we have the client FedWriters who helped us through the project to collect us with the data set and all the research papers related to recidivism and how recidivism could be reduced. So initially our phase starts at the client giving us with the documents. So these documents could be something like related to recidivism or how rehabilitation programs and treat therapies can help reduce recidivism. So these kind of documents are initially pre-processed and extracted, that is using NLP techniques like PyMu PDF and Spacey. So using these techniques, the PDF format is going to be converted into chunks of text. So later on, these chunks of text are going to be saved in Mongo database. So once this is done, alongside there's going to be embedding model. So currently we use the sentence transformer called multi-QA MPNet. So this is the newer version of the model we are using right now. And this model is going to generate each and every text that is there in the Mongo database into a dimensional vector of 768. So all these embeddings are later on stored in the Mongo database along with the text that is extracted and pre-processed earlier. So this is how it works on the database side. And once this is done, we have something called FICE vector store. So FICE is nothing but indexing package. So this is kind of, it gives each and every embedding that is present in the Mongo database. It is going to retrieve all the data from the MongoDB, that is the embeddings that is in 768 dimension. And later on, it is going to give each and every of these embeddings index so that it is easier for the LLM to fetch through the relevant documents. So now coming into the user side. So as of now, the user actually has the access to give a query to the model. So once a query is given to the model, it is going to generate embeddings to the model as well. So here we use the same sentence transformer, that is the multi-QA MPNet. So once this is done, the query embeddings are going to be retrieved by the FICE vector store. So what FICE does here is, instead of a vector database, we use FICE because it is going to be easier for retrieval. So it retrieves the documents as soon as possible once the query is given. So now coming here, once a query is gone through FICE, it is going to search for the top 5 relevant vectors that is there in the database, that is Mongo database. So since it is saved along with the content of the text, that is the extracted and pre-processed text and the embeddings, it generates all of those. And this fetched metadata text is going to be the relevant context. So along with this, we give it a prompt to the LLM, that is we are currently using OpenAI model, which is like only decoders instead of encoders. So this LLM model takes in the prompt that is, it is given a prompt saying that you are not supposed to answer any question that is not relevant to the document, or if in case any question is not, any answer is not fetched from the FIs, you're not supposed to answer it. So that is how a prompt is given to the LLM along with the relevant context, and it gives it meaning and generates a response to the user.
Nextly, data collection. In this slide, I'll explain how we collected the data needed for our project. Our goal was to provide our chatbot strong and reliable data to work with so that it can generate meaningful and accurate answers for the queries provided by the user. So we collected the data in two main ways. Firstly, we worked directly with our client. Who guided us on what kind of documents are most likely needed for residualism programs. And nextly, we have gone through publicly available resources on the internet to identify what will be the most helpful resources for the project. So by combining the expert input and trusted online sources, we've combinedly got a total of around 50 research papers. And here are a few papers. Most of them are related to CBT and ACT.
So coming to the data overview, we have collected around 50 PDF files which were related to recidivism, rehabilitation, and criminal justice. And these also included the academic papers, like the reports and more meta-analysis papers. So we choose these papers because we thought they were more relevant and informative for our project. So the documents were in the PDF format, so we had to convert them from the PDF format to the chunks of the text. So we used the NER and the TF-IDF NLP techniques so that to see what was actually there in the data, like was it related to the recidivism or not. So for our project, we choose the Mongo database for our storage to store the clean text documents. So it also provided us with the 500 MB free space. So as you can see in the picture, we have created this cluster and named it recidivism. So when you click on the connect button, it gives us a connection string. So you directly connect the string to the database. So coming to this slide, we extraction of the text. We have extracted the text from around 50 PDFs. So using the PyMe PDF. So PyMe PDF is like an NLP technique which is used to extract the content from the PDF such as text rather than the images and the tables. So this is the picture where we extracted all the 48 documents. So since it has already been extracted, you don't need to process it again. So without any repetition, the documents are processed. So when a new file is being given to the document, the text extraction is done again.
Nextly, pre-processing text. Pre-processing text was a crucial step to clean and process the extracted text for future analysis. So firstly, we started cleaning the text by removing noises such as headers and footers and references and special characters that are present in the PDFs. And nextly, we've applied tokenized the text and lemmatized the words to their root forms and got rid of all the stop words such as the, is, etc. that are present in the text. So once the text is cleaned, it is then passed through the pipeline for similarity search and embeddings.
So coming to the sentence embedding. So as of now, we chose to go with multi-QA MPNet base.version version 1. So this is a sentence transformer that includes both GPT and BERT base. So it is kind of an encoder and decoder transformer model. So this model kind of converts all of the chunks of text that are present in the Mongo database into a 768 dimensional form. So as you can see, once we run the file, that is generate embeddings. So once we run the file, it says that it checks through all of the database. So if there are any duplicate embeddings that are found, for example, there could be same file uploaded with a different name again. So these are all saved in embeddings. So it is going to search through the embeddings, and if in case there are any duplicates found, it is going to erase the duplicates. And if in case there are no duplicates found, it says no duplicates. And since all the documents are already embedded, it says that all of the documents are already embedded. So after that, we also have a file to check till now what we have done. So all the process till now, like the extraction, pre-processing, how it looks once we did the embedding as well. So as you can see, the file names are saved here along with the extracted text. And once the useless data is clean and the clean processed content is shown here. And along with that, there are embeddings, that is the vector form of a text. So that's how it is shown here. And later on, it also specifies the embedding model, that is multi-QA MPNet. So initially, we were actually working on All-Mini LM, which was also a very good model. But since the client wants it to have larger data sets, that is data that is more than 1,000 meta-analysis papers. So when we are dealing with that kind of data, this model is better for the LLM model. But All-Mini LM was also a very good model since it handles less than 100 research papers, and it does it in a very good way. So going on to FAISS, that is FACE. So face indexing and search. So what happens here? So once the sentence embeddings are generated, the face is going to fetch all of the embeddings from the database. And what it does is it initially takes in all the vectors. It is going to normalize all the vectors. That is, it finds the Euclidean distance between all the vectors. And once this is done, it is going to check for the cosine similarity. So face is going to do the normalization first, and then it checks the cosine similarity. Cosine similarity is nothing but dot product of two vectors divided by the lengths of the vector. So once this is done, it is going to give similarity score for each and every vector that is present, and this is how it looks. So once we run the face code, it is going to say that no duplicates are found again. That is, since the file is stored in a .index file, vector store.index file, it says that no duplicates are found in there, and the face is already built with 48 documents. So since it is there in dimension of 768, it shows so-and-so and the documents and so-and-so. So once this is done, we also run a sample query here for the face. So as you can see, the question is, what are the best rehabilitation methods to reduce recidivism? And it fetches through all of the index file, and it fetches the relevant documents, that is top similar score. And it gives the query as well a score, and all the documents that are there in the database are given a score. So this score given, it says that all of the models that are, all of the PDFs that are given here are kind of related to the question, and these could answer the question given by the, or given to the LLM.
Nextly, LLM. So now that we've retrieved all the relevant documents using FAISS, the next step in our project pipeline is generating meaningful answers for the queries provided by the user. And that is where our LLM comes in. So for our project, we've previously experimented with Falcon 7B Instruct LLM, but we found that to be very slow in processing the queries and generating the answers. So later, we shifted to OpenAI's LLM models, which are providing very accurate answers, and even the accuracy of the system is very well maintained with this LLM. So here's how it works. So firstly, when we provide the system with a question, the query is firstly converted into a vector with the help of sentence transformer model. And then our system searches through all the documents that are present in the database to find the most relevant ones for the query entered by the user through FAISS. And then this information is sent to the LLM. Our LLM, it doesn't just repeat the information present in the documents, but it clearly understands all the text in the documents and generates a meaningful response or a user-friendly response. This is called RAG, as it combines finding the right documents and generating a smart response. So here's a picture of our LLM chatbot interface. Once we provide, firstly, we just texted hello, and it replied in a similar way and said that it is a recidivism chatbot. And then we have given it a contextually relevant question. It goes through all the relevant documents and synthesizes the information present in the document to provide the final answer.
So coming to the backend workflow. So I have a demo video of how the backend workflow actually looks. So initially we start with connecting to the Mongo database. That is, once we connect, it says connected to Mongo database, and these are the available collections. So once this is done, we do the extraction of text, and once we run the file, it is going to check for the duplicates, and it gives a result saying that all of the files are already processed. So if in case these files are not processed earlier, it is going to get processed here. So it says since all the documents are already processed, we go with pre-processing. So once pre-processing is done, it is also going to check for the pre-processed content as well. So extracted text is going to be saved in the Mongo database along with the pre-processed text. So it also checks for duplicates there, and it says all the documents are already processed. So once this is done, we're going to generate the embeddings for the processed text. That is a clean one. So once we run the code, it also checks for all the duplicate embeddings. If in case there are any embeddings that are present, it is going to be harder for the LLM model or the face to retrieve relevant information. So checking for that is going to help the LLM model retrieve a better answer. So if in case there is the same file and it gets uploaded again, and the vectors are kind of repeated again and again. So face is going to give the same score to 3 to 4 documents at the same time. And once we try to fetch a relevant answer, it is going to give same answer like 3 to 4 times, how many ever times it is saved in the database. So once this is done, as we can see, all the 48 documents are given the file name and along with its extracted text and the pre-processed text and the vectors that how they look in vector form. So once this is done, we are going to use the face. We are going to run the code for face, and it, as we have already seen before, it is in a 768 dimensional vector. And once this is done, we also have a similar search query. So it fetches the relevant documents that are given by the related to the query. So for example, similarly, we also check if the FAIS face and both the sentence embedding model are installed or not. So once we run the LLM query, it says that FAIS is done with 48 vectors, and loading the embedding model is also done. So as you can see here, I've given a query saying what is CBT. So it is going to use face to retrieve the relevant documents, and it is going to give an information that is meaningful. So it says that CBT is kind of structured and so meaning. And these are fetched from document 2 and document 1. So that meaning this kind of question has a very closer result in document 3 and document 1. So it is later on going to be shown which documents these are as well. So as you can see here, I have given one more question, that is, how does CBT kind of help reduce recidivism? That's the main goal. So as it gives a response that is related to the answer along with the documents mentioned, this time it says that it is related to document 3 and document 5. So this is how it is going to, face is going to fetch the relevant PDFs from the database. So as you can see here, there's a small vector store.index file. So this is where all of the indexed vectors are going to be saved. So it is going to be easier for the model to retrieve information directly if in case it is deployed somewhere. So as of now, we deployed it on render. So once we run the code, these files are kind of saved right beside the main codes, and it is going to retrieve the answer as soon as possible. So there is also a negative data training done here. So if in case we give a data that is saying what does Toyota car do, so it says that I don't have enough information because none of this is related to any of the papers given before. So this is how face is going to work and generate the answer. Now going on to the LLM chatbot UI.
Now that we have our backend, it's important to have the interface. This is the chatbot interface we developed using Streamlit, and we have successfully deployed it using Render. It is a clear and interactive interface. As you can see here, when user asks a question related to recidivism, for suppose how effective are different rehabilitation programs in reducing reoffending or something, anything related to recidivism, once the question is submitted, it is sent to our backend, which runs on Fast API. Behind the scenes, the backend retrieves the relevant information from a vector database, which was built using Facebook AI similarity search as mentioned earlier. Now we have the retrieved information and the user query. The retrieved information along with the user query is given to the OpenAI language model, which will generate a context-aware, good structured answer which can be answer to that question, and that answer is displayed right here in the interface. If the user asks the negative data, like something irrelevant to recidivism about anything out of context, the system replies like, I don't have enough information to answer this and all. So this is the overall system which gives us highly readable answers all through simple chat-based interaction.
Recidivism is still a serious issue in the justice system. It doesn't just affect numbers, it affects lives, families, and communities. We designed an AI-powered chatbot that reads and understands complex documents and turns them into clear and helpful answers. This helps agencies evaluate correctional programs faster and more accurately, and also ensures compliance with the First Step Act. We believe this is a small but meaningful step towards a justice system that is more smarter, fairer, and more focused on real rehabilitation. This is the end of our presentation. Thank you, and we are happy to answer any questions.
I have two questions online, one from both from an anonymous attendee. First one is, can you specify more about the NLP techniques you implemented for RAG MongoDB-based model?
So as of now, so initially what we did was NER, TF, IDF, and LDA to check what kind of data it is. For example, it could be random research paper that is related to some other data. So if in case it is not related to recidivism, we are not going to use it in the chatbot. So that's why we use these three techniques to check what domain it is, what kind of organizations are present in it, and what kind of sections they come under. For example, NER gives it sections like one being recidivism, one being rehabilitation, one being therapy programs. So this is how the NLP is going to show what kind of data it is. So after this, we also have PIMO PDF to extract the text. So it only extracts the core content other than the images and all, and then we use Spacey to do tokenization, lemmatization, and stop words removal. Like these are the only NLP techniques we used before the sentence transformer.
Okay, there's a another question similar in vein. Suppose a user uploads a research paper on climate change or any unrelated topic. Will your chatbot still try to generate an answer? If so, what measures did you take to ensure the chatbot does not provide misleading or irrelevant responses?
Yes, so there is still, this kind of function is not yet added, but there were multiple files that we have run again and again. So one of the code base that we have run actually has this kind of functionality. Like since currently we don't have an upload functionality properly installed because we are facing many issues since we have used Phase for easier retrieval. So the render is not able to properly capture the relevant information since it is stored in GitHub. So that's why, as of now, we still didn't put in any upload option, but there is a prototype of an upload option as well along with it.
Okay, any questions in the audience? Okay. No? All right. Well, thank you very much, team.
No question.
All right. So we have an online team coming up, Team Postal Counterfeit. Could somebody from that team go ahead and share their screen?